Okay, so Martin, do you want to introduce yourself, or shall I
Yeah,
just?
absolutely, yeah. So my name's Martin Jolley. I'm a PhD student still, so I'm just a wee baby from Newcastle University. I've been focusing on surface velocimetry stuff for about 3 years now. So I like to consider myself a bit of a specialist, but I really don't know a lot compared to some of the people in the room. Today I just want to talk to you a little bit about the research I'm currently doing and how it can be applied to you guys in the field and how it can help you think about the sort of stuff that you need to consider. This morning we've already heard 2 really good talks about operational stuff and how, from experience, people have found the best ways that things work. So I'm going to build on that, and I'm hopefully going to answer a couple of questions that you had from earlier, some such things as like cross-sections, how do you know where the best cross-sections and things are? So that's actually something that I'm actually studying now. So I'm going to break down my current research into 3 separate parts. But first I want to talk about a little bit of the previous work that I've done. So I've done a placement with SEPA last year, and from that placement we actually had our own little handbook. I managed to basically put together, it's a 60-page document again. They're hefty books, but there's a lot to consider. Basically, from the research that I did previously in my PhD, which is this paper which we published last year, it basically looks at every single stage that you need to consider when you're building a site. So it goes from the site setup, the pre-processing, the processing stage, and the post-processing stage. And it breaks that down, and then the handbook basically takes all of that information that basically from the academia and the literature that's already out there. The handbook takes all of that and it applies it, and it says, okay, these are the main things that you have to think about, and this is the applicational side of it. So it builds on Mark's stuff really, really well. Also from that, I've been working with the Environment Agency recently, and we've been looking at ways of installing sites really cheaply and quickly. What's the minimum considerations you need just to get a site out there so you can start doing your own trials? So recently we developed a 10-page technical document which basically takes a really basic camera, a really basic computer, and it tells you basically step by step how to set that up and how you can start getting data from that. It also tells you how to process that data, but I've been looking a lot at KLT-IV, which is a Newcastle-based software, and also River, which is PIV lab-based on MATLAB. So the research that I've been looking at, and I want to talk to you a little bit today, I've broken it down into 3 parts. The first part of it is a sensitivity study. So the hypothesis that I have, is it worth looking at? How much does it actually impact our discharge results when we're doing our processing? All of the processing that I'm doing, I'm using KLT-IV, but basically I'm hoping that stage 2 of this research, we can start applying that to other softwares and just take the concept that I'm using and apply it to whatever you do use to process your data. Part 3 is the applicational side, and that's where we're going to start looking at cross-sections. So can we use my research? So my research basically, when we're processing our videos, whatever software you use, unless it's SDIV, SDIV is a little bit different to PIV and PTV. It basically looks on the surface, looks for traces, and maps the distance that tracer travels in a certain time. That's how you get your velocity. The stuff I'm looking at is how many traces do we need? Where do those traces need to be in comparison to our camera? Is it important that we don't have necessarily a lot of traces at one moment in the video, but a lot in another moment? So it's kind of that question of how much does it actually matter where we put our camera and how many traces we have. So that's the kind of the question that I'm trying to answer with this research. So I took 30 videos from a site in Yorkshire, in Todmorden. I processed those 30 videos using KLT. And what I did was I plotted where the start location of all of the traces were in comparison to the camera. So this graph on the right-hand side is this river. It's from that video. And it basically maps out the region of interest that we defined. And it shows you where all the traces are. So you can see that there's a big buildup of traces along the edge. I'm not 100% sure why that is. Maybe it's because there's a bigger contrast in color. I'm not 100% sure yet. But basically the idea of this is you can see there's a really good spread of traces across the river. So if we had a cross-section along here, how good is that going to be when we start processing our discharges and things? But the idea of this basically is to give us numbers and visuals on how many traces is important. So the graph on the bottom left-hand side, I map the density, so how many traces are there actually in the field of view. I map the displacement, and the dispersion. So the dispersion is basically how spread out are the traces in comparison to the area that we're looking at. And then from that, we get something called seeding density indexing. And somebody pointed out to me earlier that when I say seeding density indexing, sometimes you think artificially placed traces, and it's not. It's traces that are naturally occurring. All of this is naturally occurring stuff. It's just a basic video. So the seeding density indexing gives us a really good indication of the trade-off between what we have in our video and what the ideal density and dispersion would be. So what I do is I map those and I graph them. So the two graphs at the bottom show us two seeding density indexing. One uses numbers for ideal density based on research that's already been carried out. But the one that I'm looking at, because that research doesn't quite match up with mine, is one that I've created myself, and it basically just takes a random number from the video. So you can't compare videos between each other, but you can do a really good comparison to a video to itself. So the importance of this, basically, is from those videos, I found sections of the video where we have really good seeding density and really good dispersion. And I reprocessed those videos, but for a shorter time. So originally, the videos were 30 seconds long. I reprocessed 10-second segments of those videos and found that if you take the best and the worst 10 seconds of video, you actually get a really big difference in discharge numbers. It's about 10%, but it's a 10% improvement compared with 10 seconds of really good seeding density compared to 10 seconds of the worst seeding density in that video, which I found quite surprising because I expected the 30-second video to be the best, the good 10 seconds to be close to that, and the worst to be even worse. But what I actually found is if you look at the graph, the black line are ADCP measurements of the river that we saw before. So all of this data is from the same river. The black line is ADCP data that we got through for different stages. The blue line just underneath that is a 10-second video, which is surprising, but is the good SDI. The yellow line, which you can barely see at the bottom, is actually the 30 seconds. And the red line, which kind of does similarly map the shape of the black line, but that's the bad 10 seconds. So you actually can see that there's a good accuracy increase. But what's the most important thing for me is the variability. So using the good seeding density for 10 seconds actually reduces the variability in discharge output by quite a lot. It's about 30%. So from that, we can say using good seeding density in rivers, you can be more confident in the results that you're getting compared to, say, you go 20 meters down the river and it's not quite as good. So that was all part of the sensitivity study. So from that, I can confidently go on and start looking at the wider picture, the bigger picture, and start looking at, okay, well, what does this mean for the people who are going to be using this every day? So the quantifying impact stuff, I'm not going to go too much into this. Some of the research that I've already done, it matches some stuff that's already out there. There are different methodologies. I'm not going to go too much into that today. There's not really much point. So what I'm going to do now is compare what I found to stuff that's already out there so that I can start saying, okay, maybe we can use this between different softwares and have a little bit more confidence in it's widely applicable. But the main thing that I want to talk about today is how can we use this seed density indexing stuff day to day? It's actually, I think, we can use it really well for our cross-sections. So I asked earlier, how do you pick where your cross-sections are? And what I'm going to start looking at is, can we use seeding density indexing? So what we would do is we'd go out, we'd set up maybe a temporary camera, just get a few videos, get several different cross-sections where we're thinking about putting a site, process one of those videos, and then just get one of these graphs. So the graphs that show the density and the spreading of the traces. And actually say, okay, well, in some areas, so if we get the cross-section at the top, in some areas, we've got a higher seeding density. So why don't we try and use that as our cross-section, because we know that the higher seeding density and dispersion actually increases our discharge accuracy and reliability. So what I'm going to start doing is I'm going to start taking these videos, I'm going to start getting multiple cross-sections within a frame, mapping the seeding density and the dispersion, and seeing how much that impacts depending on where our cross-section is taken from, so that hopefully one day we can go out, get multiple cross-sections while we're in the field, and then we know later on when we're at our desks and we can use whatever the ideal is. The aim for this, I'm hopefully going to build this into the KLT software so that we don't even have to think about stuff like this, and the KLT software will pick out the best segments of the video, the best data, so that it automatically improves your data. And it also, when you click calculate discharge, it takes the best cross-section for us, so we don't even need to think about selecting and looking for ourselves. Like I said, this is all based in KLT-IV, which is a PTV software, but I'm hoping that I can make this applicable for all of the different softwares that you guys might be looking at and using. So yeah, I've already gone over a little bit of this. It's like, so what? Why does this matter? We want to increase our reliability, we want to increase our accuracy, and hopefully we can do that without thinking too much about the process of having to do that ourselves. Hopefully we can get this sort of stuff built into our softwares. It's starting to be a little bit more proven. But we can hopefully start setting benchmarks for how many traces we need to be able to see within a video to make it worthwhile using. So if we can just start doing that without even having to think about it, I think that's a massive benefit for everybody. It's a time saver, and time is money at the end of the day. And also, I've just gone across applying the best cross-section stuff just to increase our reliability in the discharge and our confidence so that we can start moving forward a lot more with this stuff. Like I just said, the end goal for all of this is to have this built in as a post-processing stage into KLT. But like I said, hopefully it can be built into other softwares, and we can start thinking about this sort of stuff as well. So we can start building these benchmarks and refusing any data that necessarily might throw us off. And also just to get some advisory information. So hopefully, and in the early days, we can just have the software pop up and say, okay, maybe you should think about using this cross-section, or the cross-sections that you have, we're not meeting the benchmark, so maybe you need to either think about moving your site, just pick up the camera and move it downstream somewhere, or think about moving your cross-section that you have. Limitations for this. So the limitations for the study that I've already done, like I said, I'm using 30-second videos as a base, and then cutting them down to 10 seconds, but as you heard Mark say earlier, they've found benchmarks saying like a minimum of 20 seconds really. So that is a limitation in my study, but I've actually found that 10 seconds of the best seeding density actually gives me more accurate and reliable results than using a 30-second video, and that's probably because it averages quite a lot. So the best 10 seconds is better than the average. So hopefully we can keep working on that and proving that. And that was my really quick talk onto my research. Did I nail the time?
Excellent. Thank you, Martin. Yeah, you've made up some time. That's brilliant. So I could just claw that time back and say, go and sit down, but I'm going to be, no, I'm going to give you the opportunity for questions. And Alex is going to save me running across the room, I think. Were you about to ask a question? Yeah.
Absolutely.
Thank you. So I understood that you compute a density of tracer, but I didn't understand how you define what a tracer is. Because, I mean, you can have several kinds of tracer that can go from bubbles to big scale turbulence patterns. So is it just a gradient of color?
Nope.
So I have another question just after. So that was the first one, and the other one is,
I'll take notes.
You can have a high density of tracer, but those tracers are not representative of the surface velocity. For example, if you have white water due to standing waves, you will have high density of tracer, but it won't be a good place for making the discharge measurement. So maybe in your analysis also should be, I mean, having a lot of tracer does not mean that it's the best place to make the measurement.
Yeah, absolutely. I've got mine. So basically, all of the traces that I've used for this study come from the results of KLT. So I'm using KLT-IV as the base, and any traces that says is successfully tracked. So it's only the ones, anything that's failed, I've disregarded. And it's basically the traces that I've used are the starting locations of those traces that were successful and were used to map the velocity. So that's where I get all my traces from. This is like a post-processing stage. So some of the research that's already out there actually uses a MATLAB code, which basically says, okay, this is a big white blob that the camera might be able to detect while it's doing its tracking. I've flipped that on its head and said, why don't we just use the traces that are actually successfully tracked? So that's where my research differs from the stuff that's already out there, and that's kind of the stage 2, comparing the two and saying, okay, how good is the stuff that you do before processing the video compared to the stuff that's being posted afterwards. So hopefully if we can get both of those agreeing, we can do a quick pre-processing, filter out anything that we necessarily might not need, and then reduce the processing time. So hopefully there's a lot of applications to this sort of research. Secondly, I think that kind of answers the second question as well, so that it's the density stuff. So yes, necessarily having a higher density doesn't improve discharge, but I think when you're looking at the early stages of this development, we don't really have anything to go off. There's a little bit of research to say what the minimum density should be, and that goes back to the research that's already out there. They've got numbers that they've found themselves from research. I want to start doing more applied stuff and saying, okay, it's really good having that from synthetic flows and artificial traces, but realistically, how good is that number going to be in the field? So I want to find a new minimum benchmark for density regarding what the best discharge you can get out of it is going to be.
Okay.
Did that answer? Cool.
Do we have another question? Martin's given a very long answer, so as to...
I'm trying to make it, yeah.
But we're going to claw back a little bit of time. But one more question for somebody? Ida, you looked as though you had a question. Liz has a question.
Yeah, no, I like where this is going because it's going to remove some of the subjectivity. Right now, there's a lot of subjectivity in the whole process and different operators making different decisions. And it's kind of all over the place, adding a lot of potential uncertainty. So I think this is a great direction to take this and like you know, build it into the software so it's happening right at the forefront, making optimized decisions in a non-subjective way. Have you seen from the data you've processed so far a big range of results? I'm curious to know like what the low, like you showed some examples of very well densely ones, but yeah, I guess maybe that's where this plot, I was curious to see like what it looked like spatially, what we're used to seeing when, you know, we're looking at a cross section, we're looking at, I think Mark had an example of the interpolation and how you're grading your measurements based on the amount of interpolation. So it's looking, yeah, what range you had.
So the interpolation is done automatically in KLT. So for this research, I've not considered too much into that. I've just let the software make those decisions for me and interpolate. And I've not graded any of these. But what I've tried to do is keep it as consistent as possible. So I benchmark everything. So this graph doesn't, this graph doesn't necessarily show just the difference between densities and dispersions. It also shows, in the statistics that I've done for it, it shows the error compared to measured, so known quantities. And it also shows the difference between the baseline 30-second video that we have. So changing those densities and the dispersions compared to what was originally done kind of answers a little bit of that, but I've not done too much depth into that sort of grading and looking at how different they can be.
Well, just because I can imagine, you know, we want to push the limits. Like how low a density can we have a reliable?
Yeah, that's hopefully everything that I'm going to answer from part 2 and part 3 of that study. And start comparing it to the stuff that's already out there because I've done a lot of that research already. So if I can find that the research that I've done matches the stuff that's already out there, I can start using the stuff that they've already done and start applying their research into this cross-sectional stuff for part 3. Fingers crossed, that's what I find. So.
Okay, brilliant. Thank you very much, Martin.
Cool.